Hello students, this is SAHA tutorial hub and today discussion about the extrema of a function, extrema, extrema of a function of two and more variables. Important topic in differential calculus, extrema, extrema of functions of function of two and or more variables, two or more variables. So here we consider just two variables, not more than two, and these are equivalent to, if you know about two variables behavior, then you can very easily find out the behavior of other variables more than two variables. So I just discuss or focus on the extrema of functions only two variables. So before starting, I of course appeal to all of you. If you have not subscribed, then subscribe this channel to get such kind of videos. And if you like, then like. And if you have any suggestion, then comment me. And if you like, then share with your friends. So let's start. First, we know a function. A function, if we consider a function of two variables, we are considering function of two variables if x y, where what what is called its maxima, when it is called its maxima if so here both the variables are independent, x and y are both independent variables. So this function is called maxima, is said to be maxima maximum if for two values, for a point x equal to a and y equal to b, for these values of x and y will be maxima if in the neighborhood of fxy, in the neighborhood of uh, ab, actually in the neighborhood of ab, the neighborhood of ab of ab, we have, so the neighborhood can be in this way. We can write down in this way neighborhood a plus delta and b plus delta, where mode of delta, where mode of delta, mode of delta to tends to 0 or just greater than 0 or tending to 0. So this in this neighborhood, if the functions if the all the all the points in the neighborhood other than at the point AB is smaller than the smaller than the point at the of the function at the point AB. Means at the point AB at the point AB the function's value must be greater than all the points all the um, values and in the neighborhood of the uh, AB AB of the function fxy. So it can be written down in this way: a plus h or a plus delta b plus delta. So where where delta mode of delta tending to 0 means there is this is a neighborhood function of this function fxy. So this at this point AB, the function's value will be extremum or maximum. Then other values of the neighborhood, other values of the function at the neighborhood. So then at this point, if AB, the function is set to maximum, and minimum equivalently it can be said minimum of exist if equivalently if it finds us that if AB is less than equal to uh, in the neighborhood of AB, the function fxy, then we can say that at the point AB, the function fxy at minimum. So this is called the function minimum for point A equal to B, where the function's value at the point AB is must be less than equal to the less than equal to of the function's value fxy in the neighborhood of AB. So if this condition happens, then we can say that fxy is set to have a minimum value at the point AB. So these are the definition of maximum and minimum of two independent variables function. So now let's see what is the necessary condition for being maxima or minima of any two variables function. Necessary condition. Necessary condition is that we can say uh, the function fxy at maxima or minima will have maxima or minima or minima or minimum values if it is satisfied that at the point x equal to a, at x equal to a and y equal to b, if the first partial derivative of the function fxy, if the first partial derivative partial derivative derivative of fxy at the point ab, fx ab, and with respect to x and with respect to y both, so both partial derivatives, first order partial derivatives, if y exist and must equal to 0, exist and must be equal to 0, and must be equal to 0. Must be equal to 0. So uh, that is, if derivative with respect to x at the point ab of the function fxy and must be equal to 0, and the partial derivative with respect to y of the function fxy at the point ab must be equal to 0. Both must be equal to 0. Then you can say that this is a necessary condition for being for having a function fxy a maxima or minima at the point ab. So its proof is very simple. I'm not discussing here. It's not too large. You can very easily understand that the if the function fxy, I'm discussing this way. If the function fxy has maxima or minima at the point fab, then fab is maxima or minima. We are considering is maxima or minima, then if we take the one variable changing and the other not, the second not, means if x where b is constant, so one variable is changing x just, so if ab is maximum, then this will be also maxima minima at the point x equal to a, at the point x equal to a. And if it happens, then the partial derivative with respect to x, if x at the point eb must be equal to 0. Similarly, if we take the other variable keeping the first variable unchanged and the second variable changing in this way. If a y, this function, if we consider at the point a, y is equal to b, y is equal to b, the partial derivative of with respect to y, the partial derivative with respect to y must be equal to 0 for having its maxima or minima. So this partial derivative with respect to equal to 0. So very easy proof. Just we need to follow that. We have to consider the function, just keeping one variable unchanged and the other variable change. And since at any point this is maximum minima, so one variable function must be um, must be the maxima or minima, and of course its partial derivative must be equal to 0. It is already proved that for one variable function fx is maxima or minima, the maxima or minima if its derivative is equal to 0. This way it can be proved. Now I consider how maxima minima uh, can be, and how we can determine that there is a maximum or minimum. How we can determine that there is certainly a maxima or there is certainly a minima. That there will be a maxima or minima. So it is found out that I am just discussing the nature, not proving this. That if the first two conditions I have already discussed, that partial derivative of the function fx y at the point ab and partial derivative of fx y at the with respect to y at the point ab must be equal to 0. This is the condition required to be maximum minimum. The other point is that second derivative at the point AB for having maxima minima multiply second derivative with respect to y at the point AB minus second derivative with respect to both variables if xy at the point AB square. So you can consider as a discriminant. So this is found that the partial derivative, second order partial derivative with respect to x or the function at the point of the function fx y at the point ab, the partial derivative with respect to y of the function fxy, or second order partial derivative of the function fxy at the point ab is multiplication so minus both partial derivative with respect to both the variables of function fxy at the point ab square must be greater than 0. If this satisfied, then we can say that fxy has maxima or minima. Fxy has maxima or minima. As maxima or minima. And if less than 0, then we can certainly say that it has no maxima minima. Means the function will be a constant function. So we can write down that if this is less than 0, if it happens it is less than 0, then the function has no maximum minimum. No maximum minimum. And if it is equal to 0, then it cannot be analyzed. And no maxima or minima. And so if for any function is found that this is equal to 0, then it cannot be analyzed. So far it cannot be analyzed. So we don't need to verify. It cannot be determined that it has a maxima or minima or not. You cannot determine if it is equal to 0. So these are the required conditions. I hope this information is useful to all of you. If it is useful, then of course comment me. And if you like these videos, then subscribe this channel. Now, of course, like in the like section. And if you have further suggestion about to lodge any video on your topic, then comment me also. Thanks for watching.